Hello, I'm Jacob Anerio, and I'll be presenting this paper called Towards Efficient Inference, Adaptively Cooperate in Heterogeneous IoT Edge Cluster. So there's been a growth in the number of IoT devices, and if you're not familiar with them, they're used in automatic driving, smart homes, and intelligent factories. So over here, I have a GIF of an automatic driving car, and then below that, I have an example of an Amazon Alexa. So, a brief introduction. Pre-trained convolutional neural networks, or CNNs, can be used in conjunction with these IoT devices to perform decision-making via inference. And then compared to the cloud, using CNNs on IoT devices have increased privacy, as well as less network pressure and inference latency on data centers. And so these CNNs have these two layers that are important in them, and then they're known as convolution layers, which are shown above, where they perform a convolution operation, as well as a max pooling layer, where they perform a max pooling operation and shrink the size of the layer. So next, there are some issues. So these IoT devices generally don't have a lot of processing power. However, attempts have been made to solve this by distributing the data to an IoT edge cluster and having each device only perform a portion of the CNN inference, reducing inference latency and memory consumption. However, this still has its own limitations. So let's start off with an analogy. So imagine we have a restaurant and they have several chefs. And then let's compare these chefs to IoT devices. And then let's say the restaurant wants to make a full course meal. In this case, we'll compare it to the CNN model. And then this CNN model, or full course meal, is composed of several copies of dishes. And so this will be each layer in the CNN. And so, for example, I have these images below of these various dishes. And then there's multiple copies of them, 3 by 3. And then this makes the final full course meal. So what exactly are the limitations that were mentioned earlier? So some steps in this process are redundant, such as gathering common ingredients for a single type of dish. Not every chef needs to be handling this, so this can be compared to redundant calculations during collaborations. And then communication is also limited due to shouting across the kitchen. In this case, this is compared to the communication overhead of the IoT devices. Then, some chefs may finish early or be overworked, and so some IoT devices may be idle or be overloaded. And so the question is, how do we optimize collaboration between these chefs, aka IoT devices, to minimize the problems above? And that's our analogy. So let's get into our proposed solution. Our proposed solution is known as PICO, or the Pipeline Cooperation Scheme. So PICO is composed of the following components. The first are continuous CNN segments that are executed in sequential order. The result from one segment is input to the next segment, and the final segment produces the output of the CNN. So we can see this here. We have our first segment, which is some convolution layers in the max pooling layer, and then there's another stage which is composed differently, and then a final stage which has a different composition. Next, you'll see that each of these segments are connected to a heterogeneous environment. And so each subcluster is going to be assigned to this segment. So this one goes here, that one goes there, and that one goes there. Then there are also inference tasks that can be parallelized and can be identical. And so you see them below. Next, Pico integrates the following algorithms to resolve the issues mentioned earlier. The first is a dynamic programming algorithm. This selects the best workload for each device in a homogeneous subcluster of IoT devices to parallelize the CNN inference, which in turn speeds up the inference process. And so next, you notice that I said homogeneous here. So we actually have to adapt this to a heterogeneous subcluster. And so this is where this greedy algorithm comes in. So this allows Pico to take into account the computing capacity of each different device. And then this in turn allows Pico to minimize redundant calculations between devices, communication overhead, idle time, and device overloading for heterogeneous IoT edge clusters. So let's start with some definitions. So we want to find the special S star such that the special S star is going to be this equation over here. And so let's define some of these special characters. So the special M is a CNN model with L layers. The special D is a heterogeneous cluster, and the special S is a stage configuration. So you might be asking what a stage is. And a stage is going to be a subset of IoT devices and CNN layers going from layer I to layer J. And then that special S is a set composed of all these stages. And then you might be wondering what this part right here is. And so that is the period of the pipeline, which is the longest time used for the stage going from I to J. And then there's the latency of the pipeline. That's the sum of the time used for all the stages. And then we also see that this over here, the latency of the pipeline, is going to be bounded by this T-lim. And so this is known as the inference limitation. And that is the definitions. Next, here's a proof. And so you may have been wondering, why do we need to split Pico into two algorithms? Why not just do dynamic programming with heterogeneous clusters of IoT devices? And so this paper introduces a proof that shows that solving for the special solution is NP-hard, and there is no algorithm for solving it in polynomial time. However, it is possible to do it in polynomial time with homogeneous IoT edge clusters. So that's why we had to split the algorithm. So now let's start with the first part of the algorithm, which is the dynamic programming algorithm. So here we change our device set to be device set prime. And then this is going to be composed of homogeneous devices that have the same average computing capacity as D. However, it still has the same number of devices as D as well. So next, we have to find this equation. And then it's still subject to the previous constraints on the other slide. And so to do that, we have to solve this. Now, let's break it down a bit since this is a kind of lots of brackets and stuff. So over here, we have P, which is going to have these three indices. And so the first indice is the starting layer. The next index is the ending layer. And then the third part is the number of configurable devices in that stage from I to J. And then there are these two parts over here. So you have the optimal sub-pipelines period, and the pipeline period was defined in the previous slide. And then the time taken to process layers J plus 1 to J with P prime edge devices. And so that's this part right here. And then we perform a min over these two ranges, and then we take the maximum of this during those mins. And so it becomes a min-max problem. Then there's the greedy algorithm. So let S prime be the solution from the dynamic programming algorithm. So we're going to let omega of I to J be the resources required to process the stage of I to J. And so we want to minimize the difference between any of these two omegas. And so how do we do this? And so this is where the greedy algorithm comes in. So we get our S prime from the dynamic programming algorithm. We sort the devices by compute capability in reverse order. And then for each device, we're going to go through and find the stage with the maximum average computing requirement. And then we're going to assign that device to work for that stage. And then we're going to assign it, we're going to put it in a specific set. And then we're going to keep doing this until all devices are assigned. And then once no devices are left unassigned, we partition the output feature map via divide and conquer to rebalance the workload. And then we return this set. Now there is one edge case we need to consider before we can continue, and that is, what if there is one stage with light workloads? And so this is where a PICO, or adaptive parallel scheme switching strategy, comes in. So this is prone to redundant computation. However, we can choose between either PICO or this one-stage solution. And by doing that, we can do it by calculating the moving average of the workload. And then we can decide whether to use the previous PICO strategy or switching to the one-stage solution based off of whatever workload is the smallest. So in our experiment, the PICO and APICO were tested along with three other systems. They are layer-wise, early fuse layer, and optimal fuse layer. And then you have some abbreviations. So for LW, there's going to be layer-by-layer network parallelization. EFL parallelizes the first few layers, convolution layers only though. And then there's OFL, which selectively fuses layers. So our experiment is shown to the right. You can see there are 8 Raspberry Pis along with one Wi-Fi router. And then 4 CNN models were tested. We have VGG-16, YOLO V2, ResNet 34, and Inception V3. So the first two are chain-based, and then the last two are graph-based. And so each graph block in the graph CNNs are treated as its own layer. And then there are several measurements taken, such as the maximum throughput, average latency, speed up, which only applies to graph-based CNNs, as well as resource utilization. And here are the results for the VGG16 cluster capacity. And so we can see that the red line, which is Pico, has the lowest inference period out of any of the 4 models tested. And so you can see that this is true for all number of edge devices from 1 to 8. And then you can also see that the throughput for the 8 devices is highest for the Pico, which is the red bars over here. And this is true for all CPU frequencies, so these 3 CPU frequencies. And then you can see similar results on the yellow V2. And so Pico is the lowest for latency. And then Pico is the highest for throughput. Now let's do the average latency under different workloads. And this is where a Pico comes in. And then we can see when the workload is small, a Pico tends to outperform Pico. And then you can see a Pico is the blue line, and then Pico is the red line again. And then the same thing over here. However, when we're testing for latency under 100% workload, we see that Pico is going to be having a smaller latency compared to a Pico. But generally it's close behind, and it looks like sometimes the error bars might overlap. Now, let's do it for yellow V2. So you see similar things over here. You can see that a Pico outperforms Pico when the workload is light, and then that's true for all these frequencies. However, something interesting happens over here where the latency is about even for 1 gigahertz and 500 megahertz for both Pico and a Pico. However, for 750 megahertz, Pico is worse than a Pico, but it looks like the error bars could overlap. So now, for the resource utilization, we see on this table over here that Pico has the highest resource utilization compared to any of the other methods. So for both VGG16 and yellow V2, so these were the chain-based CNNs. And so now let's talk about graph-based CNNs. Unfortunately, the paper does not have charts for Pico on these graph-based CNNs. However, the paper does state that Pico has a 5 times and 4 times speed up compared to ResNet 34 and Inception V3 respectively. And then you can see the speed up for these graph-based CNNs over here. And so one final thing that they tested was Pico versus getting the optimal result via breadth first search or BFS. And then on this table over here, you can see the execution costs. And then you can see as we go down here that the execution cost for BFS tends to blow up, while Pico tends to stay very small with less than a second. And however, BFS tends to have higher resource utilization compared to Pico. So Pico has less resources used on average compared to BFS, but that trade-off seems pretty well for this execution cost over here. So in conclusion, Pico uses dynamic programming in conjunction with the greedy algorithm to parallelize CNN networks, which increases throughput and reduces communication overhead and latency. And then for graph CNNs, it has higher speed-up ratios compared to other systems and methods. And then there's also aPico, which is a modification of Pico that can switch to a single stage and outperforms Pico when the workload is small. So there are some limitations to this. So the experiment uses 8 Raspberry Pi 4Bs, and so this could be changed in future works to have different edge devices with different computing capacities. And then it could also use more edge devices in the cluster compared to just 8 over here. And so the system also uses a single router, and each Raspberry Pi has the same bandwidth. And so future works could test different network configurations where the devices have different bandwidths, and there might be even more routers, and the connections may be different. And then there's no way to know in advance if the workload is light enough to require aPico in this paper. And so that could be something that a future paper investigates, whether or not you can predict in advance whether this workload will require a pico or pico. And that's it. Thank you so much for listening to the presentation.